Welcome, everyone. Today we will speak about complexity, which is a central theme for the course. And complexity comes from there are dozens of definitions. So let's say the word acquires different meanings in different contexts. But as we mentioned 2 days ago, its etymology comes from the Latin plexus, which means intertwined or braided, could be. So we can say that something complex is something that is difficult to separate. And what makes something difficult to separate? It's relevant interactions. So, for example, imagine that you have a childhood friend. I don't know, let's call him Pepe, and you know him so well that you can predict how he will behave in different situations. You know how he dresses, how he jokes, which kind of music he likes, and so on. So you could say that you have the laws of Pepe. So given certain situation, you can predict with high degree of confidence what will be the behavior of Pepe. And suddenly Pepe enters UNAM and meets Lupita, and they fall in love and they start going out. Well, first they start going out and they fall in love. Well, it doesn't matter. The thing is that we notice that our predictions start failing because suddenly Pepe takes showers more often and courses less and starts listening to Luis Miguel, and we can't understand what's going on with our friend. We had his loss and then what happened? And of course, the interactions he has with Lupita change his behavior. And it's not that the loss, let's say, it's not that he's a completely different person. It means that we hadn't considered those interactions and we didn't know how a relationship with someone like Lupita might change his behavior. And it's only when we observe a posteriori that effect of those interactions that we can start building a new theory or a new model or new laws of the behavior of Pepe. And suppose that the years pass, they get married, have a child, and this baby will not only generate new interactions with his parents that will change their behavior of each, but it will also change the nature of the interactions between Pepe and Lupita. So we can see that it becomes impossible to predict the behavior of each individual if we don't consider the interactions. And if it becomes difficult for 2-3 people, imagine trying to predict the behavior of a whole city or a whole society. And of course, we are limited in how much we can predict. Another example could be with soccer. So there might be a very good player, but if no one gives him the ball, he will never score. Or a goalkeeper, he might be very good, but without a defense, it will be more difficult to have a good performance. And on the other hand, we could have a soccer team that doesn't have any stars, let's say a star player, but the interactions are very smooth between the players, and they could, in principle, beat a team that has very good players but no coordination. And I mean, there are plenty of examples of such cases, that you have a team with, let's say, high-paid players, which makes us believe that they're very good. But then they don't have a good chemistry between themselves, and the team doesn't play good. So of course, you need both. You need good players and good interactions. Other examples could be seen with carbon, for example. So we might have full information about the properties of carbon atoms, but it depends on how these atoms are arranged, that the macroscopic properties will be defined. So depending on the molecular structure of different carbon atoms, we might have graphite or charcoal or diamonds or nanotubes or buckyballs. And each of these has very different macroscopic properties. Graphite is fragile and dark. Diamond is hard and transparent. These don't transmit electricity. Nanotubes transmit electricity very well. So it's impossible to predict the properties of the molecule if you don't consider what type of interactions, what organizations the atoms have in the molecule. And these limits our prediction. I mean, the relevance of the interactions on the system, because we can have full information about the components of a system, but if we don't know what interactions will be and what kind of information interactions will have, then we won't be able to predict the system. And this, I mean, I mentioned this is related with computational irreducibility. We'll come back to this in a few slides. But I also fact that complexity has been studied on the last, say, 3 decades and a half. It's not because people before were not aware of the relevance of complexity, simply they didn't have the tools for studying complexity. So Heinz Pechel's in a book of his from the late 80s, he says that computers are as telescopes, like telescopes for complexity. So before telescopes with our bare eyes, we can see the planets of our solar system only until Saturn, and all the satellites only our moon, and the brightest stars, and not much more. So those limitations in our sensors, we could say, or in our perception, determine how we were explaining our universe or our world. And when, let's say, Galileo's telescope was powerful enough to see the 4 largest moons of Jupiter, and as telescopes became more and more powerful, then we're able to observe more distant objects to the point that only less than a century ago, telescopes became powerful enough to observe with precision other galaxies. So before that, there was the idea that all the universe was only our galaxy. It was only with measurements that were made in the 1930s that, let's say, more distant galaxies were detected, and this redshift was detected. So then this idea that the universe was expanding and the Big Bang, let's say, it gained ground over other theories. And the same for the micro world. Before microscopes, there was the discourse that disease was caused by humors. And what's a humor? Well, it's that makes you sick. So even a century ago, in the so-called Spanish influenza of 1918, 19, and 20, they didn't know it was caused by a virus. I mean, there were microscopes, but they knew it was a virus only in the 1930s. So how can you deal with an infectious disease if you don't know what causes it? And it was only when microscopes were developed that we began to understand the cycle of different infectious diseases. And of course, there are still many things that we don't know, but let's say how computers allow us to observe complexity. Because if you want to consider interactions in a system, even if it's small, you need lots of variables. And even if we have a huge blackboard, we are limited to the number of variables that we can include in systems of differential equations. So 2, maybe 3, and it's difficult to include more variables. And and to have a systematic exploration of phase space. So with computers, suddenly we are able to explore spaces with hundreds, thousands, millions of variables. And then we can include the details that interactions bring. And then we can start to understand complexity better. And only, let's say, in the last decade, we have enough data and we have enough computing power to start including more details into our models. I mean, I will speak about this in a later class, but we're just now discovering that it makes a big difference when you consider heterogeneity in your models. So because of simplicity or computational limitations in computers until recently, or even now, many computer models, they're homogeneous in the sense that all the elements of the system are considered to be the same. But of course, in reality, that is difficult to obtain. So we have heterogeneity, and we are starting to understand what are the implications of this heterogeneity when we include it in our models. And it seems it explains many things that were considered more difficult to obtain in the study of complex systems with homogeneous models. But I mean, we'll leave that for later. And today, we will use as a guideline the text that I shared with you last week. So some of you might have read it. I invite you to go to this webpage, Complexity Explained. So this was a community effort similar to the network literacy that was coordinated by Hiroki Sayama. And so it's like a very simple introduction to concepts relevant to complex systems. And we will explain each of these concepts with examples to have a better understanding on what's complexity and why it's relevant. It has translations into Spanish and several other languages, so you can also read the translations. And many people collaborated to this effort with comments and suggestions. And I mean, we can say many things about complex systems. That's their lots of components, their interactions, they self-organize, they have multiple scales, they have distributed control, there's emergence, and the bottom line is that we need new tools, new formalisms, new frameworks to study complexity. So it's exciting that we are in a point in our history where we are developing these tools now. So there's potential to contribute to this effort. So, well, just a comic. We usually take the simple answers, not necessarily the complex one. Just a quick parenthesis, we shouldn't confuse complexity with complicated or chaotic. They're different concepts. So something complicated is something difficult, and its inverse would be easy. Something chaotic is something sensitive to initial conditions. So the inverse of chaotic could be robust or ordered, meaning that perturbations don't affect it. And something complex is something that has relevant interactions. So the inverse of something complex will be something separable. And we can have examples of combinations of systems that are complicated and complex and chaotic, or neither, or just one or two of them. So you can have all the combinations. So these are 7 concepts that are included in this Complexity Explained. Interactions, emergence, dynamics of organization, adaptation, interdisciplinarity, and methods. And as we mentioned, interactions is what characterize the complexity. It's what limits prediction. And on Tuesday, we So what are the philosophical implications of considering interactions as real, whatever reality is? Let's say that they have causal influence on the physical world. So perhaps some of you know the game of life. It was proposed more than 50 years ago by John Conway, who died a couple of years ago. And let me switch. Well, no, first let me explain the rules of the game of life. So it's a cellular automaton, meaning that it has cells. Basically, you have a grid or a matrix, and the squares or the elements of this matrix can take values 0 or 1. In this case, we can represent 0 as the cell is dead and 1 the cell is alive. And then it's an automaton because there are rules that determine how the states will evolve in time. And these rules are very simple. So if around a live cell, meaning there is a 1, we count from its 8 neighbors how many are alive. If they have too many, then it will die because, I don't know, there's not enough food or oxygen or whatever, and then it dies. And if there are too few, or it's alone, I don't know, it's too cold or loneliness, whatever, it also dies. So in order for a cell to stay alive, there has to be only 2 or 3 neighbors in the possible 8. It doesn't matter where, just that there are 2 or 3. Less than 2, it will die. More than 3, it will die. So that's the transition from 0 to 1. And transition, from the transition from 1 to 0. And the birth transition 1 to 0, it's when there are exactly 3 neighbors around a dead cell. Then there will be a new cell arising there. Okay, so let me shift to a game of life simulator, which is called Goalie. You can download it for free. It's open source. And every time I share the screen, the Zoom screen disappears. But anyway, yes. Am I sharing the right screen?
I'm seeing a white line.
Yeah, let me try again. I think that's better.
Yeah.
Okay, so we have our grid, and we can make a cell alive, and sorry, I'll just change the speed. So if there's 1 cell, it dies because it doesn't have neighbors. If there are 2 cells, let me zoom it a bit more. If there are 2 cells, then both cells die because there are not just 1 neighbor, so you need 2 or 3. If you have 3 cells, you have an oscillating structure because, let me pause it. The one in the center, it has 2 neighbors, so that doesn't die. The ones in the extremes have only 1 neighbor, so they will die. But then in these ones next to the center, there are 3 neighbors, so there will be birth going on here. So that's a oscillator of period 2, and it stays there forever. So if we add another one and we have 4, it evolves into a stable structure, which has each cell has 2 neighbors. So let's say time passes and nothing changes, no deaths or births. Let me add another cell, and we could say, aha, reproduction. So it multiplies, and now we have 4 honeycombs, they're called. We add another cell. And there's some activity. And there are some stable structures like these cubes where each cell has 3 neighbors, so they're stable. And then there's activity, and let's say they get destroyed in time. Well, the system is deterministic. There's no noise. The rules are very well defined. Then we can see some regular patterns. And here we can see that there are some structures that move in space. So these are called gliders. They move in diagonal. And in the rules, there's nothing telling us that there will be movement. I mean, it's not hard-coded in the rules. So we can say that this is an emergent property. We'll see a bit more about emergence. But basically, movement is a property that arises from the interactions between the components. And of course, we observe it at a different scale than the cells because it's a pattern of several cells. And let me go here. So this is an example of an initial condition that has only 7 cells. So we could assume that we have very simple rules, very simple initial conditions, and we should be able to predict easily what will happen. And well, let's see what kind of behavior it has. So there's some patterns, some activity, some gliders going to infinity. It has open boundaries, the simulation. So we can see that it's difficult to predict what patterns will arise from an initial condition because we have to go through all the intermediate steps. We don't know how a cell in time, let's say 1000, will affect or not affect other cells or other structures in the future. So even if we don't want to predict the precise pattern or even the number of cells, we could try to predict simply how long will it take for the system to stabilize, meaning that the population will not change because there are birth and deaths going on. And we might ask, well, will it stabilize? Well, in principle, it should stabilize because let's say it's, but not necessarily. It could be there are some patterns that grow infinitely, but in most cases it does stabilize. But if we want to predict how long it will take to stabilize, we don't know. I mean, it's more than 5,000 generations. Well, now it's stabilized. So basically, we just have to wait and see. And now it's stabilized, and then we can say, oh yes, of course. When you start with this initial condition, then it will take 5,000 and something generations to stabilize. There's a whole zoo of structures. Let me just show some. So, for example, let me show some others. Yeah, this one. So these are different spaceships, which there are structures that move in space at different speeds, and we can see, and then we can interfere with them, and they're very fragile, so we just destroy them with a single change. There are also other structures that eat spaceships or gliders. And there are others that generate these structures, like there are glider guns, which are smaller, but these are some spaceships that generate gliders. And then the gliders, when they collide, they build glider guns. So you have structures that generate structures that generate structures that generate structures. Yeah, this example never stabilizes. It keeps on growing infinitely. So Fernando asked in the chat whether this program is kept here. I mean, the game of life by itself, no, but there are forest fire models that are based on cellular automata, and in Goalie you can run several cellular automata. In NetLogo